So thanks for the organizers for organizing the conference and for the invitation. I've learned a lot just from the talks and from the discussions, and I'm quite excited to talk about some work I've done with two fantastic collaborators, both of whom are postdocs at MIT, Hotat Lam and Omar Aksoy. And this is work that we put out on arXiv in September. So let me start off with something I think everyone in this room cares about, which is that a fundamental problem in quantum field theory or CMT or high energy physics is to understand quantum phases. For instance, we want to know how to diagnose different quantum phases. How can we tell if two quantum phases are different or the same? We also want to know what are the possible allowed quantum phases. And sometimes we get quite lucky and we come across phases that are characterized by symmetries. Maybe like a superfluid and a U1 symmetry, or a TI and a U1 in time reversal. And we get lucky because for these types of phases, the symmetries provide answers to 1 and 2. They tell us how to distinguish quantum phases and how to classify quantum phases. So what's been quite interesting for me with this generalized symmetries boom in the past 5 or 10 years has been understanding the relationship between quantum phases and generalized symmetries. And there's like if you're given a generalized symmetry, you can kind of build a phase. There's some recipe. And the recipe goes that you choose your generalized symmetry adjectives. So maybe like N-form symmetry, you choose it to be invertible or non-invertible, dipole, subsystem, whatever your adjectives are. And then you specify the symmetry breaking pattern and the SPT pattern. Okay. So if you follow this recipe, you can obviously choose the adjectives to be not generalized, this ordinary symmetries, and you get your ordered phases like the superfluid and the TIs. So we recover our old friends, but then we quickly recover things that are quite interesting. We see that we get phases with topological order, we get things with fractons or Higgs phases, and then when you start getting really wild, you come across phases that just don't have a name. Okay. So I think it's important to understand which quantum phases are characterized by generalized symmetries. And in this endeavor, phrasing quantum phases in terms of generalized symmetries, we get a unifying and novel perspective of quantum phases. Right? In this list of quantum phases, there's a topological insulator next to a fracton, and there's a unified way to understand both at the same time. It's also guidance towards new quantum phases and models that realize them. Right? And on the bottom, these phases that we haven't named yet, it's not because we found them like 30 years ago and we were just too bored to give them a name. It's because we never found them. And then lastly, something that's been mentioned is this generalized Landau paradigm. And as we better understand symmetries, maybe there's a dream that we can start to classify all phases of matter by symmetries. And in this talk, it's mostly about the second point. We're going to use symmetries to give us new quantum phases and find models for those new quantum phases. So in particular, everything in this talk will be in 1 plus 1D, and we'll talk about SPT phases. And these SPT phases, they'll be protected by translations and some non-invertible symmetries. Everything will be on the lattice. If you're a field theorist, I don't want you to decouple, so please ask questions if you want translations, not these translations. And this is the punchline. For the experts, because some of the heroes of the SPT stories are in the audience, the punchline is we'll talk about a new class of SPTs. They're entangled weak SPTs, and they're characterized by projective non-invertible symmetries. If you know what these words mean, entangled and weak SPTs seems to be contradictory. We'll find that they both happen at the same time. And projective symmetries in SPTs also seems contradictory. Usually if you have a projective symmetry, you can't have an SPT. So we'll find that that's also possible. And the rough outline of the talk will be, we'll first review SPTs. We'll really emphasize a symmetry defect perspective. It's kind of closer to how we think about SPTs in field theory. And then we'll give a simple example of this class of SPTs in an exactly solvable lattice model. And then we'll generalize a little bit and make some more general statements. Okay. So without further ado, in this talk, when I say an SPT, I mean that there is a phase of matter with a gapped ground state, a gapped unique ground state on all spatial manifolds that's protected by a symmetry. Okay. And what's cool about SPTs is that we can have interesting physics that arise on boundaries of SPTs or interfaces between SPTs. So there's often a Tufts anomalies. Yes, Leo.
Same thing as SPT with projective representation. Is that the same thing as SET, or should I think of it as SET, where there's
No, think of it as an SPT, but the symmetries are in some projective representation. Usually projective representation forbids an SPT.
Okay.
Hopefully it's yeah. Hopefully it's
Okay.
clear. We'll get
We'll
there
see how it
naturally.
goes.
We'll get there
Okay.
naturally.
Thank you.
Okay. So while there's interesting physics at boundaries and interfaces, SPTs can still be characterized in the bulk, and they're characterized by their response to some static probes. So usually these static probes are things like background gauge fields. Like the first SPT I ever learned about was the difference between an ordinary insulator in 3+1D and a topological insulator. And you turn on a background gauge field for some U1 symmetry, and you see that the response theories are different. This is ordinary Maxwell theory, E squared minus B squared. And this is Maxwell theory with a theta term, E dot B. So we can tell the difference between these two SPTs by this E dot B topological response. But maybe people aren't as used to symmetry defects as the probe. So let me review some things about symmetry defects, mostly from the perspective of a lattice. If you're used to QFT, think of these symmetry defects as the topological defects you know and love extended in the time direction. Okay. So the definition of a symmetry defect is some localized modification to my theory. And this localized modification will modify the Hamiltonian and all other operators in the theory. And this sigma here is just some subspace, maybe like a loop, that the modification is localized about. So for example, in this picture, the modification will be localized as a red loop. And one of the defining things about symmetry defects, there's a bunch of defects, but the defining thing about symmetry defects is that you move them using unitary operators. So that's to say, if I have my Hamiltonian with a defect inserted along this sigma 1, I can move it using some unitary operator and conjugating the Hamiltonian. So for example, maybe it takes this domain wall here to the domain wall over here using this unitary operator. Okay. And for this reason, the spectrum doesn't depend on where the topological defect is or where the symmetry defect is. And for that reason, people tend to call them topological defects because you can infinitesimally wiggle them and it doesn't change any of the physics. Okay. This is different than the notion of topological defect that comes from having some field and having defects characterized by the topology of the field. Yes, Leo. Yeah.
That are modified in the defect Hamiltonian.
Yeah.
And now I apply this unitary. Then the Hamiltonian on the left-hand side, that defect is now appearing in a different location, correct?
That's right.
For example. Yeah. So, I mean, strictly speaking, they're not the same Hamiltonian, right?
But they're unitarily related. So the energy spectrum doesn't know any difference. So
right.
Yeah, if you.
But strictly speaking, that H on the left-hand side is H prime. It's not the same Hamiltonian.
Oh yeah, it's different Hamiltonians. The difference is the fact that they're labeled by different sigma 1s and sigma 2s.
Oh, I'm sorry, I didn't see 1 and 2. Okay,
yeah,
thank
it's okay.
you.
Yeah, and the next, maybe 2 slides from now, I'll show an example. Okay. So when I start moving these symmetry defects around, what they'll do is they'll implement the symmetry transformation in space. So for example, suppose I have some creation operator, some fermion maybe, that's acting on this position R, and I have a symmetry defect for the U1 symmetry. If I move it through the operator will be transformed by the U1 symmetry transformation. Okay. And this gives a very fruitful perspective of symmetry defects, is that they're generally related to twisted boundary conditions. I have like a domain wall. I translate my whole system back to itself as kind of like I sweep my domain wall through the system, and I transform everything by that symmetry transformation. Okay. Good. So let's see this in action, specifically in the context of probably the simplest SPT on the lattice. This is going to be an SPT with a Z2 times Z2 symmetry. And we'll consider a closed chain in space. And on each site, J, there'll be 2 qubits. Okay. And these qubits will be acted on by the Pauli operators, X and Z, and X tilde, Z tilde. And I want to consider 2 Hamiltonians. And all of the examples right now are kind of simple examples. Maybe they're not interesting. The first Hamiltonian is just a normal paramagnet. And it's exactly solvable. The ground state is just a tensor product of all these states in the X equals 1 and X tilde equals 1 state. The other Hamiltonian is the cluster state Hamiltonian. It's also exactly solvable. And the ground state satisfies these relations. Okay. So if you've never seen these Hamiltonians before, don't worry. The point is these are simple examples that you could convince yourself that they have unique symmetric gapped ground states. Okay? And you can further convince yourself that these Hamiltonians, they have a lot of symmetries, but here are two things here are two of the symmetries I want to focus on. The symmetry U and the symmetry operator U tilde. You can easily check they both commute with a Hamiltonian, and they act on both of these ground states just by a +1. Okay? So we have two gapped Hamiltonians with a single ground state, and they have symmetries. By the definition I gave, they're SPTs. Okay? But now we ask the more important question. Are these the same, or are they different SPTs? Right? If they're the same SPT, I could go from this Hamiltonian to this Hamiltonian with symmetric deformations without closing a gap, without undergoing a phase transition. And let's use this symmetry defect perspective. I'm going to insert a symmetry defect for the U symmetry operator. And there's a lot of things that will change when I do this, but we can guide ourselves by noticing that it'll give rise to the twisted boundary conditions. Right? U is a product of x's, so as I go around the system, a single z operator will get transformed by a minus sign. Okay. So the paramagnet Hamiltonian, this guy doesn't have any z's in the Hamiltonian, so it isn't modified. And because it's not modified, the ground states aren't modified. They satisfy the same relations. However, the cluster state Hamiltonian, that did have z's. In particular, look at this guy. This guy's a j plus 1. So when j is equal to L, this will be a z acting on L plus 1. And now I use my twisted boundary conditions like an extra minus sign. I have a different Hamiltonian. And I can rewrite this Hamiltonian as the following. It's just the cluster state Hamiltonian plus this localized deformation near the link L and 1. Okay. So this is our symmetry defect. And the Hamiltonian is still exactly solvable. And you can find the new ground state. And the new ground state satisfies different properties. It's still a +1 eigenvalue of U, but now it's a -1 eigenvalue of U tilde. So these two SPTs have different responses to the U symmetry defect. Therefore, they are different SPTs. Just like how in the insulator example, they had different responses to the U1 gauge field, and we call them different SPTs for that reason. In particular, with this first SPT, I inserted a U symmetry defect and saw that the ground state still carries U tilde equals 1 symmetry charge. With the second SPT, the U symmetry defect carried non-trivial U tilde symmetry charge. So we can distinguish the SPTs by the symmetry charge carried by the domain walls in the ground state. And this is exactly how we think about it in field theory. If we wanted to discuss these in field theory, we would distinguish these two SPTs in terms of these invertible topological field theories. And the whole point of, so if we say that this is z equals 1, the HP model, the HC model differs from the z equals 1 theory by this invertible phase. And what this invertible phase does is when I insert a defect network of these symmetry defects, it'll assign a +1 or a -1 given by the parity of the intersection number. Okay. Yes.
Sorry, maybe a trivial question, but are you calling also trivially gapped vacuum also like a trivial SPT? Or?
Yes.
Oh. So like the ZP is a trivially gapped.
Yeah, you could call it trivial. If you're really getting down to the weeds, though, there isn't a canonical choice of trivial always. It's kind of like a spin structure. You can classify spin structures, and you tempted to say it's classified by some cohomology class. But really, it's the differences of spin structures that are classified by cohomology. It's the same thing with SPTs.
But I mean, to be sure, so you don't have an additional case which is trivial gapped in all your possibilities. Trivially gapped is the same as trivial SPT for you.
Yeah.
Okay.
Yes, yeah. Yeah, another question over there.
Thanks. From the point of view of entanglement, you know that both ground states are quite different, right? Because one is a product state and the other one is short range as expected, but it's non-zero, right? So it's possible there is any connection saying that looking at the entanglement is guiding you in order to say there are different SPTs?
Yeah, for this example, that's definitely true. The examples we'll cover later, the SPT-LSM theorem, is that there'll be SPTs that always have non-trivial entanglement. So that perspective will actually fall short for the class of SPTs we'll get to.
Okay, it's a very concrete example.
Yeah, Leo.
And everything you talked about on the lattice where you don't have gauge fields, is it somehow that gauge fields is encoding this twisting?
Good. The way I would suggest to think about the gauge fields is there's a one-to-one correspondence between a background Z2 gauge field and some Z2 domain wall. And this corresponds formalized in what's called Poincare duality. If I have some Z2 gauge field and it's only pointing in the x direction, only the x component is non-zero, it implies that there's a Z2 domain wall in the time direction. So that's how the gauge fields are secretly there on the lattice, because we know we can insert these defects on the lattice. And then we use this correspondence between defects and gauge fields, more precisely the location of the defect. And that's how we can make connections to this. I'll be happy to talk more about it though.
So non-trivial gauge field in that field theory formula corresponds to non-trivial defect, inserting a defect.
Yeah, in space-time, it would be a non-trivial, it would be a non-contractible Z2 defect line in space-time.
And what does the union of A and A tilde mean?
So that's not the union. It's something that's like a generalized wedge product. So think of this like a wedge product. It's called the cup product.
Okay.
It's just there because these aren't really differential forms. They're what's called cocycles.
Okay.
Okay. The cup product to cocycles is like the wedge product for a differential form.
Okay. Thank you.
Yes, you're welcome. Another question.
So if given a symmetry operator, do we know a systematic construction of the defect in Hamiltonian? So because here you're using the Z2 example, and we are very clear about the corresponding defect, which is just the sign flip in front of Z. So if for a generic symmetry operator, what does it look like?
Yeah, I don't know a systematic procedure that works for any symmetry operator.
Okay.
I know how to do it for certain types of non-invertible symmetries. I can talk to you about that later.
Okay.
But I don't know for a complete general one.
I see. Thank you.
Yeah. Okay. Thank you for the questions. Good. So that was our first example. And now let's go to one more quick example. It's an example that's more important for the SPTs we'll talk about after this. So again, we'll be on a 1D closed chain. Now there's a single qubit on every site, and we'll consider these two Hamiltonians. They're very boring, but it's just a demonstrative example. And they're both paramagnets, but the sign in front of the Hamiltonians are different. Obviously, they both have unique gap ground states. We can label them by plus or minus, whether or not it's x equals 1 or x equals minus 1. And these have a bunch of symmetries, but the symmetries I'm going to care about is a Z2 symmetry and lattice translations. So we have a gapped Hamiltonian. It has symmetries. So by the definition I gave, it's an SPT. I'm going to actually use a slightly different, or I'm going to use a terminology people use in the literature. And in that, an SPT characterized by lattice translations is called a weak SPT. It's not because this SPT isn't lifting enough weights. It's because if you add spatial disorder, it breaks the translation. So it's weak to spatial disorder. So with this terminology, H plus and H minus are both in Z2 weak SPT phases. But now we ask the question that we asked before. Are they the same? Or are they different SPT phases? And let's proceed just as before as well. So we'll insert the symmetry defect. It'll give rise to the twisted boundary conditions, but neither of the Hamiltonians depend on Z. So the Hamiltonians definitely aren't modified. The ground states definitely aren't modified. But we insert a symmetry defect. We do more than just modify the Hamiltonian. We modify all the operators, including the translation operator. Physically, you can think of this modification as, suppose I have a defect right where I'm standing, and I translate my system. I'm going to move the defect with me, right? The Hamiltonian gets changed. I need to have a modification to my translation operator that does only move the defect back. So this defect-free translation moves the defect. This x1 moves the defect back if the defect was at this site or that link, okay? And in fact, the fact that you have twisted boundary conditions, you already know that there has to be a modified translation operator, because the ordinary translation operator, this satisfies t to the L equals 1. Okay. Good? So now let's see, are these the same or different SPTs? So I'm going to restrict for L even for a second. And then what we find is that U acts on both ground states by a +1, but T, whether or not there's a Z2 symmetry defect, acts differently. So when there is a Z2 symmetry defect and we use this modified, this twisted translation operator, now we see there's a difference in how the ground state responds. And we can understand that as the Z2 symmetry defect in the minus ground state carries some crystal momentum. It carries a non-trivial eigenvalue of the translation operator. Okay. So we know they're different Z2 weak SPTs, but there's another perspective which, let's remove the Z2 symmetry defect and go from even L to odd L. When we go to odd L, if you remember, this is a product of x's. Now, sometimes you get a +1 or a -1, depending on if the ground state has x is equal all 1 or x is equal all -1. So again, we see that there's some response happening when we change from even to odd system size.
Thanks for the hard work. So just so I see, so very naive questions. So just to be sure, so you have a Hamiltonian and then you insert U. And did I understand correctly, the Hamiltonian changes?
No, not in this example. Neither H plus or H minus are modified.
So did I then understand correctly that U has, for example, no energy? Because you have the Hamiltonian somehow in my naive world characterizes the energy. You add something to the system, which is U.
But I'm really changing the theory globally. I mean,
Okay, so you would say it's
I would say there are different theories globally. One has a defect, one doesn't have a defect. I think if I have a CFT and I insert a defect, technically I have like some defect CFT. Obviously they're related to one another, but they have different global properties.
Okay, so okay.
Well, we can talk more about it though.
No, thanks.
Yeah. Okay. So how should we interpret this last row? Well, we can interpret it as the translation defect carries a non-trivial Z2 charge. The reason why is, remember, before I insert a defect, I always have ordinary periodic boundary conditions. And one way I could think of insert the symmetry defect is going to twisted boundary conditions. Now I have the symmetry operator appearing on the right. But this is just, for the translation symmetry, this is just ordinary periodic boundary conditions if I just remove a site or add a site. Okay? So going from even to odd, it's just like inserting a translation defect. So I go from a plus sign to a minus sign in the GS minus state. Yeah, Alexi, there's a question.
Sorry that you're getting so many questions, but it's because it's super interesting. Can this be interpreted as a 't Hooft anomaly between the Z2 symmetry and translations?
Good. No.
Interesting.
Yeah. This is only true acting on the ground state. It's not true at the level of the whole Hilbert space. Yeah. But that's a very important point. Yeah. And people, yeah. Anyways. Okay. Good. So that was a quick warm up. Now let's get into some of the new stuff. And what I want to start off with is some curious Hamiltonian. We'll show in 1D, but now we'll have a single qubit and now a Z4 qubit on each site. The qubits you're already familiar with. The Z4 qubits, these are clock and shift operators. They to the 4th power equal 1. And the clock and shift operators don't anti-commute. They fail to commute by a I. Okay. And the Hamiltonian I want to consider is the following. It looks a little scary, but it's just some nearest neighbor Hamiltonian. Okay. This C operator here is just an operator that conjugates X in Z. Okay. So if you stare at this Hamiltonian long enough, you'll see it's a sum of commuting terms, so it's exactly solvable. Furthermore, you can check that it has a unique gap ground state. Okay. And then you could solve for that unique gap ground state. And this, if anyone has trust issues, let me show you what it is. This is what it looks like. It's always going to be in the background of our head. And now we can say, well, I have a gapped Hamiltonian. What are its symmetries? Right, that's kind of the perspective we're taking. What are the symmetries? And we see if it's an SPT or not. Well, here are the symmetries I want to care about. So there's certainly lattice translations, translation variant Hamiltonian. You look at this a little bit longer, you find there's 3 Z2 operators that commute with the Hamiltonian, made out of x squared, sigma z, z squared. So we have some Z2 times Z2 times Z2 symmetry. And now you really look at the Hamiltonian. And maybe you like, go to a mountaintop and ask the universe what the symmetries are. And the universe, tells you this operator commutes with the Hamiltonian. And you say, wow, thank you, universe. That's so kind of you to tell me. It looks kind of gross. Let me tell, for people maybe have a QI background, you can write this as an MPO with bond dimension 2. It's manifestly translation invariant in this form, and the MPO tensor is just made out of Z's and sigma Z's. Okay. But if you really start it, you can check it commutes with the Hamiltonian. And the interesting thing about it is that it's a non-invertible operator. Okay. Why is that? Well, suppose I have some state where R1, one of the Z2 symmetry operators, acts as a minus sign, or R2 for that matter. Well, look at these projectors here. If that's true, then RE acts on the state as a 0. So the operator has a non-trivial kernel, so it doesn't have an inverse. Okay. Good. So we have a non-invertible symmetry. And now we can ask, well, what is this non-invertible symmetry? I go to my best friend on the street and I want to tell them I found a non-invertible symmetry. What's the label I should give it? Well, you can check that the symmetry operators obey the following. U squares to 1. All the RIs square to 1. That's their Z2 operators. And then you can check that RE, that non-invertible guy, it doesn't square to a single operator, but a sum of operators. Okay. And then furthermore, RE kind of absorbs the RIs both from the left and the right. Okay. So if you wanted a label for it, we'd say, well, this is a Z2 operator, so we call it Z2. And this forms a fusion ring of a fusion category, which is rep D8. It's just these operator identities look the same as the tensor products of the representations of D8. So that's where the name comes from. Don't sweat it if you don't like it. That's just the name we're going to be calling the symmetry. Okay. But it's not only Z2 times rep D8. There's this funny business that's going on. Depending on if L is even or odd, the operators can anti-commute. So we're going to call it a projective Z2 times rep D8. Okay. So how do these operators act on the ground states? Well, T, U, and R1 just act as +1. Okay, that's kind of boring. R2 acts like this. If L is even, it's a +1. If L is odd, it's a -1. That's a lot like the weak Z2 SPT example that we're used to. But now we get something new, which is that RE acts as a +2 if it's even, but then it annihilates the ground state if it's odd. So that's weird. That's something inherent to non-invertible symmetries. You can never get this with an invertible symmetry. So what we can see is that we have the Hamiltonian that's in a Z2 times rep D8 weak SPT phase. That's just the symmetries that we have in the game. And is characterized by the translation defects carrying this rep D8 symmetry charge. Right? Because when I when I went from L even to L odd, that's like inserting a translation defect. Okay. And as a spoiler, this has consequences. And the consequences is that it constrains the entanglement patterns of these ground states. Yes, Leo.
Symmetries. Maybe one slide back. You had this. Yeah, you had the U, R1, and R2. Those are ordinary symmetries, right?
Yeah, ordinary Z2 symmetries, like an Ising
right.
symmetry.
So what I missed is how did the RE arose? I mean, I know you can write it down, but you saying the Hamiltonian is not invariant to U, R1, and R2?
Oh, the Hamiltonian commutes with all of these operators.
But you're saying in addition to those 3 Z2s, there's also this additional RE operator.
Yes. And it also commutes with the Hamiltonian.
And it's somehow not an obvious one.
Yeah. We didn't find it because we started with this. Actually, we found it because we started with this MPO. So if you're kind of using this MPO perspective, it's a little bit more obvious. This is kind of like just a product of little MPO tensors, so it's more natural to guess from that perspective. So for some reason, if you want to write it in terms of this, it looks kind of unintuitive and scary.
I guess I'm just wondering, like, I have a lattice Hamiltonian.
Yeah.
Like you were discussing earlier. And I look at obvious symmetries, various translations, spin flips, global spin flips, and how do I know that there's maybe a hidden another non-obvious symmetry like your RE that's and I'm just not clever enough to find it. But you
I mean, I don't think there's any systematic way to find all the symmetries of a Hamiltonian. Like sometimes you have some physical intuition that tells you. One thing we can talk more about after is sometimes there's some duality transformation. And you go to a Hamiltonian where the symmetry is kind of obvious, and then you do the duality transformation, and you kind of just see you get something gross like this.
But you have some intuition for what this RE do? What does it do?
Yeah, this RE is actually kind of like it induces the Kramers-Wannier transformation of this R1 and R2.
I see.
Of those Z2s. Yeah.
I see. Okay, thank you.
Yeah, you're welcome. Yeah, another question. Oh, yes.
Hi. Sorry. I'm wondering if there is any connection between this kind of model with the cluster state model, because that cluster state model also has this replicate symmetry.
Yeah, so the cluster state model, so it would be more like a D8 times rep D8.
Yeah.
Yeah, so there's different symmetries, different SPTs. So I don't know of any relation. Yeah.
Oh, okay. Thank you.
Sorry, just a quick question. Do you ever can you write in terms of background field this weak SPTs? Or,
I don't know what the background fields for rep D8 is.
Well, then my question is for the previous example where you had just invertible symmetries and translations. Can you write?
Yeah, you can write it in terms of the background Z2 gauge field for the Z2 symmetry. And then there's kind of two paths. One, you can just imagine the translations like an invertible symmetry, and you can turn on that invertible internal symmetry background field. Another path is to take the translations more literally, and you actually add a foliation structure in space-time. Okay. Then there's some foliated field. And the SPT is kind of like A wedge product E, where A is the background field for Z2, E is this foliation background field. It's like equipping some structure on space-time.
Thanks.
Oh, just a quick question.
Yeah,
previously, you said that in the last model that a translation does not carries a non-zero Z2 charge. That's only true for ground state, so it's not a 't Hooft anomaly. But in this case, is this a 't Hooft anomaly, or can you gauge the rapid asymmetry just alone?
Yeah, there's certainly no 't Hooft anomaly here, right? If I have an 't Hooft anomaly, I can't have an SPT.
Yeah.
So the fact I have an SPT means there's no 't Hooft anomaly. So that's the first thing. The other thing is you can gauge the rep D8 and you see you have a dual D8. But I think the fact, you see you have an SPT, there's no 't Hooft anomaly, that's kind of the end of the story.
I see, thank you.
Again, a naive question. So in this setup, are all symmetries completely democratic to you, or some of them more useful than others? Is there some notion like this in this
I love all symmetries equally.
Sorry?
I love all symmetries equally.
Okay, so it's not like some of them are, easier to compute in this setup or something like this?
Some look nicer, but I don't have any, besides like some aesthetic distinguishing feature.
Okay. I thought like more like practically. Sometimes, for example, like non-invertible symmetries seem like they are always as powerful as the original continuous symmetry system.
Yeah, I don't know. This will be, we have a non-invertible symmetry characterizing SPT. That seems just as powerful as an ordinary symmetry.
Okay, so. I see. Thank you.
Yeah. Okay. Thank you for the questions. Good. Okay, good. So I emphasize that there's this projectivity involved, and I want that to be a surprise. Actually, when we first saw the projectivity, we thought it's impossible to have an SPT because we were using intuition about invertible symmetries. Let's just recall the invertible symmetry reason. If I have some projective symmetry where these are both unitary operators, I can't have an SPT. And the proof is very simple. You first assume that there is a non-degenerate symmetric ground state, and then you quickly arrive at a contradiction. U times U2 would act as 1, and then U1 times... But then if you flip the order of this and you get a phase, then you'll get a phase. So certainly this can't be allowed. So what gives? What saves the day? And what saves the day is the non-invertibility. There's a loophole. So hopefully everyone can see the equation on the bottom. When L is even, I don't have to have any projectivity. It's just gone. So when L is odd, how can I still have this be compatible? Well, I can just have a unique gapped ground state that is annihilated by the operator, right? Then you just get 0 equals 0, and there's no contradiction there anymore. right? So on this slide, the fact it's equal to 0 when L is odd, that has to be true. That has to be true. Okay. Let me see how I'm doing on time. Okay. Okay, so we saw this particular example. It's a cool example, exactly solvable. You get a lot of intuition from it. But now let's take a little bit of a step back and try to see what generally is going on. Maybe not the most general level, but a fairly general level. So this projective Z2 times rep D8 symmetry is a special case of a projective Z of G times rep G symmetry. G is a finite group, and Z of G is the center of that finite group. So it's just a subgroup of the group of all elements that commute with one another. For D8, the center is a Z2, so that's why we had a Z2 here. And rep D8, mathematically, it's a fusion category of representations of the group. But for all intents and purposes, it's just some, it's just a label that tells you that we have symmetry operators that are labeled by E-reps of the group, and we multiply them together. We get a sum of operators with these multiplicative coefficients that are the same coefficients that appear when you look at the tensor product of representations. Okay, so it's just a label, and you can easily prove that whenever the finite group G is non-abelian, the rep G symmetry is a non-invertible symmetry. Okay, so we had G equals D8, order 8 dihedral group. That's non-abelian, so that's why we had a non-invertible symmetry. Okay, so that's the Z2 times rep D8 part, but where's the projectivity part? Well, the projectivity generally arises through a relation like this. The R and the U operators don't always commute. And they fail to commute by some phase that is depending on the system size. And the phase particulars is given by this. So this is like the character of the group element Z in E rep gamma divided by the dimension of that E rep. So let's look at some examples. So suppose we had G equals Z2. Well, there's two E reps, and the center is Z2 itself, and so there's two elements. And this phase is trivial for all the elements except for the bottom right guy. Okay. Yeah, question.
That means the graph state has to be in the kernel of this, right? It has to be in the kernel.
Yeah, it will have to, if there is an SPT.
Yeah, but how about like high excited state? You don't really care, right?
Yeah, right now I'm just trying to look at SPTs by how their ground state responds. Yeah, so we haven't investigated excited states above the SPT.
Okay, thank you.
Yeah, and there's a question with Leo back there.
Of G and
that's right.
Rep of G.
Yeah.
So, but then in the specific example, you had D8.
That's right.
So what I'm trying to understand is what is the, could I have it in retrospect deduce that or guess that it's D8? Like where's D8 coming from if you looked at the original Hamiltonian? Like in the general notation, there's a relation between those two arguments, but here there's no relation between D8 and Z2.
Yeah, here's one way you could have gotten D8. You could have done some sort of like Kramers-Wanier or like some Kennedy-Tasaki transformation, and you would have seen that the resulting Hamiltonian has a D8 symmetry. And there's actually a relationship between D8 and rep D8 through these types of transformations.
I see.
So that's one way you could have had some intuition that there is a rep D8 there.
Okay, thank you.
Cool. Okay. Can I have like maybe 5 more minutes or so? There's a lot of questions. So. Okay. Good. And then for the D8 example, there's only one -1 sign. It's the -1 sign that we saw before. Okay, and let me just comment that there's an explicit expression for these operators if you consider a Hilbert space whose local dimension is the size of the finite group. Okay. This U operator just kind of multiplies all the group elements belonging to each site by the group element Z, and this is some diagonal matrix. Just has this with numbers given by the character of the product of all the group elements. Okay. So let's focus in on this equation. Well, whenever there is an R gamma that's a unitary operator, then this becomes a projective algebra of unitary operators, and the normal arguments for why there should be no SPT go through. Okay, so we can have SPT phases when all the R gammas that are unitary have these phases be trivial. So when we have these SPT phases, the projective algebra still plays an important role and it gives rise to an SPT-LSM theorem. So the SPT-LSM theorem just states that all SPT states have to have non-zero entanglement. And it's kind of a consequence from this fact that this projective algebra forces any SPT state to be annihilated by the non-invertible symmetry when the phase is non-zero. So but before I end, let me just kind of quickly go through the arguments for the SPT-LSM theorem. To prove it, what we can do is we'll use the following. So firstly, Z of G is an anomaly-free symmetry. It's on-site, so we're going to use that to our advantage. So this is a product of local operators in a linear representation of Z of G. And these local operators will satisfy this algebra. And then we'll make an assumption. We're going to assume that any unique gap ground state will not be annihilated by the non-invertible operator at some special system size. And this will be a special system size in which the phase is equal to 1. Okay. So it's actually easy to prove this assumption if we have this particular Hilbert space. We don't know how to prove it for a generic Hilbert space, but actually you can argue that as long as it flows with some TQFT description at long wavelength, this has to be true. Because in a TQFT, the vacuum is never annihilated by a non-invertible symmetry operator. It returns the quantum dimension of the non-invertible symmetry operator. Okay, so those are the two assumptions. And then we could prove this SPT-LSM theorem by finding a contradiction. So if there is a unique gap ground state, that's a product state, where firstly the local Z of G symmetry operators will be equal to 1 or maybe some phase. And then we'll use that assumption that there's some special system size for where R doesn't annihilate the ground state. And then we undergo some contradiction. So this can't be true at this system size. So there can't be an SPT state that's an ordinary product state at L equals to L stars. But this further implies, if the Hamiltonian is local, that there can't be an SPT state that's a product state for any L. Because if we had an SPT state that was a product state at some L that wasn't L star, then we just add on extra product states to get to the SPT state that would have existed at L star. But we just proved that can't happen. So therefore, this can't happen either. So therefore, this projective non-invertible symmetry prevents a product state SPT, and all SPTs have to have non-trivial entanglement. And something that we argue, which I can show you guys later if you want to, is that the projectivity always causes the translation defects to carry a non-trivial rep G charge. Okay, good. So this is a summary. Let me not go through it. If you want to read it, you can. But let me just emphasize, it's a cool example. I think we're better understanding SPTs with non-invertible symmetries. But I really hope the takeaway message of the talk is that we can find new quantum phases and new models once we start using generalized symmetries as a guiding principle. Okay, so thank you for the questions and your attention. And if there's any more questions, I'll be happy to answer.
I talk. What happens if you have more than one non-invertible operator? So you have like RE1 and RE2. Is this something interesting?
Yeah, so I mean, the rep DA example only had one non-invertible operator. But there will certainly be, for general rep G, there will be choices of G that has multiple non-invertible operators. Yeah, I don't think anything qualitatively new happens in that case.
And then on your example now, like you can think about in terms of like qubit, but do you think any type like Rydberg atom experiment that can realize this symmetry?
I think it would be very interesting. I don't see any fundamental reasons that couldn't exist, but it's not something I've tried to work out with a realization yet. But I think it'd be very interesting to try to do that.
Hi. So if I think of this abstractly, I have some projective category structure. A priori, that has nothing to do with translation or the number of sides on the ring. So I guess there are stories that are unrelated to translation as well, right?
Yeah.
But like so how do you incorporate translation into the projectiveness here?
Good. Maybe there's two comments to make. Firstly, the general message that the projectivity allows for an SPT doesn't care about translations at all. So that's one thing to note. You're spot on with that. There's something more complicated though. I don't think the normal fusion or categorical description of symmetries works generically on a lattice. One thing that you know with fusion categories is that the fusion ring is always positive coefficients. But for a lattice, that doesn't have to be the case. Well, why? In relativistic QFT, you can argue by unitarity that it has to be positive. But just on a quantum lattice model, I don't see any reason that has to be true. So there's some even more general structure, even without including the translations, that I don't know what it is.
Yeah, category certainly is more general than fusion category. For sure.
Yeah. It's just usually for 1 plus 1D, people would say it's a fusion categorical symmetry.
Right. But yeah, I agree that it can be more general than fusion category. But like, how do you incorporate translation into it when you?
Yeah, I don't know. Here's another issue with translations. Usually, we always have the symmetry defects be localized. That's an important part. The translation defects, if I just have a single translation defect, it's fine. It's like a local, I'm removing one site. That's a localized modification. But what if I wanted the translation defect for like L over 2? Okay, then I'm removing something like half the system size. It's not really localized anymore. So I don't know how to think about the defects in that case. So this is to say I don't know the answer.
So these are discovered by actually trying out an example, or is it like how do you incorporate the translation into the projectiveness?
Yeah, this was discovered just by some examples. Yeah. Actually, I didn't talk about it, but we really guided ourselves with something called G-qudits. So there's like generalizations of the Pauli operators for degrees of freedom that are labeled by elements of a finite group, and that was really the guiding principle. And then we happened to stumble upon this while doing that. So
thanks.
Yeah, thank you, everyone.